by Yeon Lee, who works at the Germany. I think you were working in Germany. Is that true, Yeon? But she's part of the BepiColombo team in the ESA mission, and she's been analyzing data from the BepiColombo flybys of Venus, and she will be talking today about measuring Venus brightness and why this is important.
Yeah, thank you very much, Ricardo, and thank you very much for the organizers for this nice opportunity to introduce the measuring Venus brightness. Yeah, and okay, so actually, yeah, okay, I'm a Venus researcher, but I'm in that somehow transition between two institutes. So I was working in Germany before, and I'm going to move to South Korean Institute later this year. And thanks to this workshop, this online workshop, I'm able to join from northern city Kiruna in Sweden. And okay, so that's just somehow some chatting, and I would like to go back to the scientific talk here. Wait a second. So I believe you are able to see my mouse cursor. And yeah,
yes,
okay.
we can see the mouse. We can see the mouse.
Yeah, thank you very much. So the measuring Venus brightness is it's not so easy because Venus is so bright. If we use big telescopes, it's easily saturated, but it becomes a very nice target to use small telescopes because Venus is bright. And I like to introduce this work was done by the big team effort during the 2020 Venus dayside observation team. This team is composed by the 3 spacecraft teams and the 6 ground-based telescope teams, and I'm going to introduce briefly, one of the slides later. That first, I like to tell you that why we need to understand the Venus brightness. So first thing that I like to tell you is that the Venus brightness shows short-term variations. These short-term variations is connected with the atmospheric global scale dynamics as shown in the previous talk, Emmanuel's talk, but a bit slightly different. This wave is mostly explained with the Kelvin type wave or the Rossby type waves. This fluctuation periodicity changes between 4 or 5 days periodicities between these two. And this left plot showing the Venus as seen the first color composite using these 3 wavelengths. These images are taken by the JAXA's Akatsuki Venus orbiter on board. The 2 cameras has been used for this image composite. And as you can see, sometimes here Venus appears reddish and next day bluish. And one day appears as a reddish and next day appears as bluish. And so these fluctuations are has been plotted in the right side as the exact difference that the brightness deviations, and the same wavelengths. These 3 wavelengths plots are shown here, and this near infrared is shown in this yellow line, shows the bright, dark. Here is missing data, the bright and dark. This fluctuation could be up to plus minus or 20%, and this fluctuation actually means the cloud top altitude seems to be changed over time at the higher cloud top, lower cloud top, and then higher cloud top and lower cloud top altitude. Such fluctuation can be estimated from this brightness and near infrared wavelength brightness. And at the same time, we see UV brightness changed in the other way around. When the near infrared bright, UV brightness appeared to be dark. When near infrared brightness is dark, yeah, UV brightness appeared to be bright. So it means when the cloud top altitude changes up and down, the unknown observer okay, so UV observers correspond to they are very sensitive at these two wavelengths, and their abundance changes together, but it changes brightness the other way around from the near infrared brightness. So this type of the brightness tracking will be quite important to understand the vertical motion at the global scale atmospheric wave activities. Another important thing that we need to understand Venus brightness is about energy budget of the planetary atmosphere. So this figure shows the 365 nanometer UV albedo of Venus over the long period of time. As you can see, this y-axis shows the year. So over more than 10 years of time, we compared actually 4 spacecraft measurements: the Venus Express, Akatsuki, the Messenger, and the Hubble Space Telescope data. And this plot shows that the 3 of them, and showing the albedo, UV albedo at low latitude changed quite drastically over this decadal time period. And these Hubble Space Telescope data points are quite well overlap each other. And this trend seems to be global. So not only for the low latitude, high latitude albedo seems to be changed together. And such a variable UV albedo is caused by abundance of unidentified UV observer that exists in the cloud top level. And this unknown observer is a very important source of solar heating in the atmosphere. And its abundance changes means there is a significant heating rate changes in the atmosphere. I like to tell you that what does it mean that the heating rate changes? For that one, I like to show you this plot. So Venus is as a very slow solid body rotating planet. That Venus may have the very simple global scale one big circular, the global scale circulation cells, so-called Hadley circulation cell. And this type of the global scale circulations is governed by excessive heating in the global scale. And so you can perhaps imagine very easily that on Earth, equatorial region definitely has the excessive solar heating rate, and because the lower the solar insolation angles, higher latitude becomes a bit colder. And so very similar thing, actually the same phenomenon occurs also on Venus, but the heating, the maximum heating occurs at the cloud level because of this unknown observer. So this unknown observer seems to change in its abundance over time. So when there is a more abundant unknown observer exists, then solar heating, solar energy supposed to be observed strongly. More photons will be observed by the unknown observer, and this can cause stronger heating, and it can pump up this upwelling motion, and the strength of the Hadley circulation can be stronger than before. And such phenomena we could explain using the global circulation model calculations led by the Sébastien Lenovois, the colleague in France, and we could successfully explain from the albedo change, heating rate change, and consequent heat or the wind speed changes over decadal period. So that's the reason that we need to understand how is that the variations of brightness, Venus brightness over time, either short term or long term. And there was a quite exciting one opportunity to make some big collaborative Venus observations thanks to the BepiColombo mission. So BepiColombo is ESA JAXA's Mercury orbiter, and it's in the cruise phase currently. But during this cruise phase, BepiColombo is able to observe Venus from far away, and such an opportunity happened in 2020, first time. So BepiColombo observed Venus from 0.3 AU distance and was moving in this arrow direction. And at the same time, Akatsuki Venus orbiter was located between the planet and the sun. And at the same time, Earth, the ground-based observations were possible to make Venus imaging and the take the spectrometer data as well from 0.8 AU distance. So using all of these three location observations, we try to understand how is the Venus brightness over broad wavelength range and also from different scattering geometries. So here it shows that our campaign team, the 3 spacecraft and the 6 ground-based telescopes are listed here. And I really thank all of these colleagues participating in this campaign and made about the really valuable data of Venus to understand Venus atmosphere better. And for today's talk, I like to focus on these 2 measurements, the CAHA 2 observatory 1.23 meter telescope and the STELLA 1.2 meter telescope observations. And here, this slide shows the example images of the STELLA 1.2 meter telescope. So yeah, here the example images is shown here that the Venus image is taken at U-band. I have to say, okay, that compared to the previous talk, the morphology is not that well visible, but our emphasis is on the brightness measurement. And the colleague in Potsdam, Thomas Granzel, made excellent quality of the Venus U-band brightness data. And this data actually covered quite long period of time between August and November in 2020, and was able to measure the magnitude of Venus at U-band as a function of solar phase angle. The solar phase angle means that the angle between the sun, planet, and the Earth. This angle is a kind of the hint to understand that how the scattering properties and to understand the aerosol properties or observers distributions. So I'd like to tell you that actually this U-band imaging, this U-band magnitude measurement is the first time after Irving's study. So it's the first U-band magnitude measurement in 50 years. It's quite surprising because Venus is a very bright object. We can see Venus so easily, but in between, nobody tried to measure Venus brightness, to quantify its brightness. Here, the Malama et al., the more recent paper is proposing U-band magnitude, but this is kind of some estimation. It's not based on the observation. So the real observation before our campaign, actually is this one, the blue curve Irving study. But unfortunately, that the bandwidth used in Irving's study and our study are quite different each other. So our next goal is that we would like to cover longer term period and want to first to understand that the mean phase curve properties to understand that where would be the unknown observer's vertical location in the clouds using the shape of the phase curve. another data was taken by CAHA 1.23 meter CCD camera, and again these data were taken by colleagues in Germany, Stefano Motola and Stefan Hemi. They made excellent quality of the flux measurement that the photometry data of Venus at 4 channels, as shown in these vertical lines. And this data set is shown in these red dots here. And when you compare with the previous studies measurement, the phase curve seems to be quite well consistent each other. I was quite happy to see these consistencies with the previous study and the latest observations. So then how we use this brightness. So here I'm showing you the example. So using those ground-based data sets, the STELLA U band and the CAHA to CCD 4 bands are shown here. And using these ground-based images, we could compare relative spectral data, relative reflectivity of the Venus measured by the bigger telescope, the CAHA to 3.5 meter telescope data, and also the spacecraft data sets taken from the Akatsuki data, the 2A3 and the 365 nanometer channels. And using these observations, we could construct the structure of the cloud, and we could make somehow simulations, some expected reflectivity of Venus as a function of wavelengths. So you can recognize that the simulation and the observations show somehow difference. This difference is caused by the unknown observer, and we could extract how much observation is caused by the unknown observer in this plot. So as a function of wavelengths, our study, this solid black curve is the retrieved observation caused by the unknown observer during the campaign time. And it's a quite good news is this result seems to be quite consistent with the previous study, Perez Hojas et al. Study, using the messenger Venus flyby data at low latitude in 2007. This consistency is quite good news, but we see a considerable difference between the observations and the model assumptions, as shown in these the green and orange curves. These orange and the green curves are the data that assumed to calculate solar heating rate. And this difference means we will need to update unknown observers observation spectra to understand solar heating rate better. And we can estimate that how is the temporal variabilities during the campaign period. So this plot shows the fluctuations as a function of time. And these bottom two data sets are taken from the spacecraft. And as you can see, it has a very good the temporal resolutions. And we can recognize the up and down short-term fluctuations. And above the 1, 2, 3, 4, 5 lines are taken from the ground-based telescopes. And the good news is that from U-band brightness, we can recognize somehow this local fluctuation seems to be consistent with the spacecraft, but there is a bit of time lag, like about 1 or 1.5 difference between the spacecraft measurement peak and the ground-based measurement peak. This is caused by different field geometry. The ground-based observation was mostly watching the morning side, and the spacecraft at the time was mostly watching afternoon or evening side. So this difference caused is the reason of this bit of time lag. So here is the somehow summary. So Venus is too bright for big telescopes, but it will be a good target to use small telescopes. And the small telescopes measured flux can be a very good reference to analyze spectral measurement by big telescopes, and it can play a crucial role in physical interpretations of data obtained by big telescopes and spacecraft. And I like to tell you about the next Venus dayside campaign opportunities. It's coming quite soon. In June and July, there will be a next opportunity to make Venus observations together with Akatsuki and BepiColombo. And from May to July, as you can see, this y-axis, top plot y-axis shows the solar local time, and the BepiColombo in red line, and the Akatsuki in black line, and the Earth observation in blue line. They are almost overlapped over like 4 to 3 months. And this will be a good opportunity to compare the brightness measured from 3 locations. So please consider to join this next Venus brightness measurement campaign. And if you need more details, please feel free to contact me in this email address. Yeah, thank you very much.
Thank you, Jeonju. This is very interesting. So part of the observations were done with the DLR camera in the Calar Alto Observatory. Is that right?
That's right.
Because that's one of the telescopes that is offered and one of the instruments that is offered through the Europlanet Telescope Network. And so if someone is interested, they could apply through the Europlanet Telescope Network to get this data and help you in the analysis, getting a better view of how Venus is changing its brightness. So that's a good possibility. And I think that in the table, there could be other telescopes too, but certainly that is one of those. Is there any questions from the audience?
I have a question.
Yes, Manus, please.
I would like you to tell us, what do you expect from amateurs? What is the methodology to make observation useful for you?
Yeah, that part. So for this type of the brightness measurement, we actually do not need much detail of the morphology. We need star observations together at the same air mass, similar air mass, to correct the brightness of Venus. So important measurement that the basic will be Venus observation and the star observation together should be done for this the brightness measurement.
So I guess it's like a photometry of variable stars.
That's right, exactly.
Yeah, it's just that you have a bigger target, and it's not more difficult than that, but precision is difficult. It's here, there was one question by you.
Yes, actually, I want to ask Jeonju a question that is from Andre Kovacs. He's asking in the Discord platform, but I can read the question to you, Jeonju.
Oh, yeah, thank you.
He's asking about recommendations about platforms or databases from where amateurs can download or even where they can upload disk integrated photometry of Venus or a spectra. Do you know any database, any platform?
Oh, that's connected with previous study, previous talk actually, and I think that
exactly.
Yeah, the PVOL website, I think is a really well organized website, and I think Javier wrote the link in the chat.
Yeah, in that database, normally we are not having that kind of data because normally we are getting images, but we could try to work in incorporating that kind of data through the Europlanet. So PVOL is also is funded by the Europlanet research infrastructure, and we can try to do things in that sense if there is interest from the people. So Andre, I have his email. I can email him and get back to this question later on. So we'll have to move on. And our next talk is in a completely different subject. We are going now to community issues, and we have a